1, 2, 3. Oh, hello. Just some quick reminders before the next talk starts. There are still some shirts available at Reg. Please buy a shirt. I don't want to take any home. Similarly, a bunch of the folks in the vendor hall are going to start wrapping up soon, so if you wanted anything from them or from lockpicking or from hardware hacking, the Learn to Solder kits, etc., they're going to start packing those up pretty soon after this talk. So check those out before everything's gone. Additionally, most of the contests, if you're doing any contests, end at 4 p.m., so wrap whatever you're doing up for those. 5 o'clock will be closing remarks in this room, and then the after party will be at Null Space Labs later tonight over in Burbank, just a short drive away. Coming up next, we have Nate Singer with Interpret This, Hunting for Bugs in the Python Interpreter.
Well, hello, everybody. Thank you for coming to my talk today. This is going to be an overview of the Python interpreter architecture, and then I've got 3 bugs that are still currently unpatched in the production release of Python that we'll go through. I want to say that some of these bugs are like, some are more impactful, some are less impactful, but I think they give good context on the general strategy for finding bugs. So the focus is more about the research strategy and what led to actually locating these. With that said, a little bit of background on myself. So I came from originally traditional IT security background, so system administration kind of stuff, and then eventually moved into more cloud work, some K8 stuff more recently, and specifically on autonomous vehicles. So if anybody's working on autonomy right now, I'm probably interested in talking to you after. We're doing some really cool stuff in the autonomy space, and then also some avionics and SATCOM sort of space things as well. More recently, I've been interested in like ML and AI spaces, and then I run a national youth competition called Hackabit, and I'll be talking about that in a second. But that's been hugely fulfilling for me recently, working with lots of high schoolers across the country. So with that said, before we get into the content of the presentation, I wanted to just bring this up because I think there's a good audience for it here. I'm looking for educators and sponsors for our next year of competition. And so if you're interested in teaching, we are looking for folks in a variety of different areas, from programming to networking to general computing, and a lot of things in between. And so please come find me after if that sounds appealing, and we can talk about what that looks like. And then if your organizations are looking for really high quality things to sponsor, I think that we've got something good to offer. Cool. So coverage for today. We've got the Python interpreter design at 1,000 feet. So we're going to go through what CPython looks like at a high level. And then we'll talk about a research strategy for actually finding those bugs that we were talking at the beginning. And we'll go through 3 bugs that we have just as a discussion and a way to talk through some of that strategy. So there's a cache poisoning bug, a few overflows in the stable ABI, and then some typosquatting stuff in pip3. Pip is, of course, adjacent to Python, technically speaking, but it's still maintained by PSF, the software foundation that organizes Python. And so I think they're relevant to talk about. So let's get into the different types of interpreters that we have available to us, and then some just overview of how the things are managed. So some of this might be a little small. I'm going to go through it. If you guys want the slides at the end, they'll be available for you. So CPython is the most common version of Python that you've probably used. It's the native and sort of default implementation. It's written in C, and it's the reference implementation of Python. With that said, when we run source code in Python, we can also run it in other ways. So there's MicroPython for smaller embedded systems, JPython or Jython for running Python in web browsers, actually, or with JavaScript. There's IronPython for .NET, and Stackless is another variation of this, right? So there's a lot of these, but as you probably can't see, it's probably too small. The CPython project had about 120 merged pull requests this month. JPython had 0. So they're maintained at different levels. You know, MicroPython's somewhere in the middle at around 30. And if you look at the contributions on these projects, you can see There's just different levels of maintenance, right? So CPython is by far the most popular implementation of Python, and it's what we're going to be talking about today. And so there is a team behind Python. It is relatively small. They only do about $3 million of annual revenue. We're a project that's supporting millions and millions and millions of developers every year. And PyCon is the way that they raise that money primarily. So they run a conference called PyCon across the country, and this is how they generate money. But they're responsible for maintaining integration of PRs, all the security behind Python, the PSRT, which is the security and response team, as well as any sort of like CVEs we would integrate, that kind of stuff. So the point here is that they're very small, and we're going to see the impact of this later. So with that said, let's get into CPython. So CPython is the focus today. We're going to start with abstract syntax trees, interpretation, and compilation of source code. We'll talk about what we consider to actually be within the scope of CPython, and then we'll talk about how we maintain and change code in this project. So this is probably the single most important thing to understand in regards to getting from source code to instructions on a CPU. The abstract syntax tree is a way that we can take a syntactical statement like x equals 1 plus 2 and turn it into something that can be turned into bytecode and then compiled into instructions, right? So in this case, you can see we're using the native AST library, and we're going to parse out x equals 1 plus 2, and we'll dump the parsing of that, and we get this string that says it's got a body of an assignment to symbol x, and we're going to store a value in that, and then we're going to store a binary operation of left constant 1 and right constant 2. And so you can imagine how this scales out. And on the right, again, this is probably a little bit small. On the right, you can see a tool called instaviz. This is not a native Python library, but it's something that we can use to visualize this a little bit easier. And so using instaviz, we can open a small web app and then view the AST for an entire library or tool that we've built. And so here you can see I've clicked on one of the ones at the bottom here. Let's see. This guy right here. And then we get this node property on the right. And so this is essentially the same thing you're seeing on the left, but we can view it all the way up to the top of the tree. And so you can imagine how this turns into source code, because we need something to tokenize the syntax before we can turn it into actual like opcodes on CPU. And from a code standpoint, again, this is mostly for your reference. We're going to talk through verbally here. The first step is to go from source to an AST, and then the second step is to go from AST to bytecode. And then that bytecode is what gets interpreted into instructions. So on the left, you can see we've got just general context, so it's going to pull system configuration and any command line flags that we give it. It's going to take the script, or we could also provide this as like -C and some syntax directly on the command line. We'll then build a Py object, which is a combination of the AST that we just talked about, as well as some symbols. And then we take this Unicode Py object and actually build an AST out of it. And so this is what starts the whole process of being able to generate bytecode. And then from there, we can take that Py object, which has the AST in it, and run this run eval code object function, and that'll take that and start turning that into bytecode. So you don't need to understand this at a very low level right now. This is just conceptually, these concepts are important. And so for scope, what we're going to be talking about considering as CPython today is the interpreter itself, of course, as well as native libraries. So this would be things like OS or AST. Sys, for example, are all Python native libraries. And then we also have the pip package manager, which, as I said at the beginning, is sort of adjacent to CPython, but it's also maintained by PSF and is very closely related for a lot of the stuff that we do. So the last bug is something that we could talk about in the context of pip. Okay, and then the last thing before we get into research strategy here is how code is maintained. So if we want to change something in Python, it's an open source project, and so we would fork down the repository, make our changes, and submit a PR, just like any other open source project. If we want to submit a security fix that is sensitive, though, where we can't just, we don't want it to be public domain until it's fixed, we would stage this up for pcert, and we would email them. They have a GPG key that we can use. The problem here is that like we mentioned at the beginning, the Python team is very small. So they can handle these, but they're only willing to handle like top tier, remote code execution, pre-auth RC type of stuff. And so if you have, like the bugs that we're talking about today, they're not willing to handle at their level. So it's stuff that we're going to have to submit PRs for and fix sort of ourselves. Or they're just not going to get changed. And if you look at the bottom here, there's this one PR from September 2005 that is still open. You can find this on the CPython project, as well as one from 2010. And these are security implications. They're not just bugs. And so you can see it takes a certain level of seriousness for the PCert team to actually handle something themselves, which makes sense. All right, so research strategy. We're going to talk about building a threat model for CPython. We're going to look at comment analysis. There's a ton of really interesting comments in the project that are public domain, of course. And then we'll talk about some linting and static analysis tools, although I have limited belief in some of that stuff. But it's still good context. So this is kind of how I've personally modeled CPython in terms of the threat model. We're going to go, and this will probably help conceptualize some of the stuff we just talked about. We start with input gathering. So this could be a source file, or it could be right on the command line. We're going to take some sort of Python syntax, and we're going to abstract that into an AST so that we have tokens. So we're going to lex that into an AST. And from that lexed AST, we're going to take that and generate bytecode, and eventually execute that bytecode as instructions on the processor. And so we have the ability to input files, configuration, any sort of command line stuff here. We also have libraries that are going to get inserted here, right, as bytecode is generated. And a lot of this stuff is already bytecode. It's already cached. And we'll look at an attack there. And then we have execution of bytecode, so any of our local PyCache that's cached, or any device information coming from local devices. So like you can think dev slash type of stuff would be here as well. And then on the output side, we have a process that gets generated initially. There's going to be cache generation that happens with the bytecode here. This is where we get our PyCache from. And then we have additional cache generation here to update things. There's going to be we're going to consume system memory and CPU, and we're going to also have device interaction either with network sockets or anything else you can imagine here. So this may not be perfect. This is my high-level attempt at this. I'm sure things can be changed and worked on here, but it's a good starting point. And so there's a lot of really interesting discussion for open source projects because there needs to be to get anything done. And so people will bring up issues. You can see for CPython we have about 5,000 open issues, and then that gets merged through PRs. So we've got about 1,500 open PRs and 27 project boards that have a variety of just kind of forum discussion on them as well. And so we can look through this to find ideas for what to go after. And trend analysis can be really interesting because we can look for things that have been problematic over time. We can look for things that keep coming up or modules that have a lot of issues in them, inferring that maybe the code is not the best. Also, for PRs, there's a way to sort this, so we can look at different types of PRs. We can look at security issues specifically. We can look at bugs in specific areas. So if we, for example, were curious about finding something in like an HTTP library, we could look for PRs that are focused on web traffic, right? So there's lots of different things here, like SQL is an example here, so there's lots of SQL interaction that we could mess with potentially. And then the last thing is discussion boards. So this is either things where people are just kind of like, curious about something. Maybe there's not an issue, but they want to develop a feature. And so we can use these boards to conceptually look at different things that might be coming up soon, or just things that have been bugging developers because maybe a feature doesn't exist. And these can lead to security issues or security implications down the line. So an example of this actually is there's a lot of discussion on one of these boards about encoding issues. And one of the I didn't attack this, but there's a hash collision attack essentially because they're using a algorithm that is limited to the sense where if you use anything, an input over like 6 characters, you potentially are going to get collisions. And so that came from one of these boards. There's lots of interesting stuff in there. And often they will just tell us. So if you grep or Control F for overflow, it comes up a bunch of times. If you grep for problem, even like the word problem comes up a bunch of times. You can grep for like vulnerable, and use your imagination here. There's lots of options. But there's tons of examples of this, and this actually led to the first bug that we're going to talk about in a little bit. But before that, the last thing before we get to the first bug, static analysis tools can be good as well. Obviously, we have the full source code. We don't need to reverse this from compiled stripped binary. So we do have all the symbols we would need. We know the source is good. There's no reversing element, right? So the static analysis tools can be useful. I personally just don't enjoy using these because you're going to get a bunch of things. You're going to get maybe 1,000 issues raised by the tool, and maybe like 1 or 2 of them are actually interesting. And so you have to be able to sort through them. I think it's more efficient to just go after the bugs through other means. But these are certainly an option. For the Python side, PyLint, and then for the C side, which is probably more interesting in this case, we have the Clang Power toolset. And that brings us to our first bug. So the first bug is a cache poisoning attack. And so like we talked about, Python has to generate a cache for efficiency reasons. And then we're going to talk about the exploitation side of this and how we might fix this in the future. So this is what the optimization looks like. Python is relatively slow compared to a language like C. And this is generally because creating a stack frame is very expensive. So you have to set up a base pointer, a stack pointer. Maybe you have stack canaries involved. It's fairly complex from the standpoint of actually just getting to a point where you can start executing code. When you're in C, if you write a function, even if you're making system calls, it's probably faster and dramatically faster a lot of the time. And so Python has to do certain things to speed up execution of code in order to make it competitive for a lot of these problem sets. And so bytecode caching, where we actually have bytecode and we save it to disk, is one of the ways that we do this. There's also something called the stable ABI or the C API for Python. The stable ABI being the long-term support version of that that can be used to save some of the stuff. And then we have compiler optimizations just as you wouldn't see. So there's a book called the Dragon Book that's very famous for compiler sort of theory. And we can talk about that offline if people are interested with that. And so this infers, right, that we can control the cache somehow. Like there's something that happens that results in a cache object being created, either in memory or on disk. And potentially we can manipulate that. And this is stored in a __ PyCache _ directory relevant or like referenced, co-located to the source code. And so in a normal control flow, we would have execution of script.py. This would get lexed into an AST, compiled into bytecode, and then the bytecode gets executed. In the case of this optimized version, we run script.py. Python says, hey, I already have a PyCache for this. And then that PyCache gets executed directly. So there's no lexing, there's no compilation into bytecode that has to happen. And that's a massive speed improvement. So if we look at our threat model, we can cross off the whole first 3 steps. And we're just looking at execution of bytecode, so we don't have to worry about abstraction through a ton of this code. We can just look at the specific modules that are actually executing the cache. And that's super, super valuable for looking at bugs, because we have more control, essentially. It's about getting as much control as we can for a lot of these problems. And so in this case, we're just going to modify the cache and get execution here. And Python is really concerned about having deterministic PyCaches. So it wants to know that when you run source code, you're going to get reasonable bytecode, and it's going to be the same every time you generate bytecode for that same source. And so these Python improvement specifications, Python enhancement proposals, PEPs, are ways that we generate new features in Python. And PEP 552 specifies deterministic PYCS. And so we can look at this whole PEP. If you're interested, you can go online and see this. But the core component is that they specify this new class, and it is a bit field where instead of just using a timestamp, now we have the option to use either a checked hash or an unchecked hash. Interestingly, though, while this was implemented in 2017, on the current main branch of Python in 3.12, the one that's actively being developed, this is still not implemented. So this is available for use, but it still defaults back to the old timestamp. And we're going to abuse this in a second. So if you look at the actual header, we have a magic number that represents the version of the interpreter. So this would be all the way down to like patch versions, so 3.12.x. whatever. And this magic byte can be pulled from import lib, which we're doing here. We then have a check bit. So this is what I was talking about coming from this class. And so this bit field is a value 0 through 3, or 0 through 2, right? 0, 1, 2. And so 0 would be a timestamp. And as you can see, this header is from a real PyCache I pulled a few weeks ago. It is all zeros. So this is saying that this header is a timestamp validation. And of course, to generate that timestamp validation, we can use some Python code. And I know this is probably too small to read up here. Don't worry about it. Trust that this is a timestamp. And then we also have a source file size at the end, which is more recent. But importantly, all that we're doing here is validating a timestamp. And so you can probably see where this is going. We're going to generate malicious bytecode. We're going to copy in the original header or generate it ourselves. And then we're going to replace the original cache with our updated file that contains malicious code. And so because the header is only validating this timestamp, and it's not validating that a hash in the header is actually representative of the cached bytecode, we can use this to do interesting things. And so let's look at a POC. So I'll talk through this. The important thing here is on the right, this header, it's the first 4 bytes, so first 16 bits, or first 32 bits. And this is not going to change. So when we inject our payload, you'll notice this first line does not change, and that's what matters. Okay? And then on the left, all this is we've got a hello world application. So in the library, we define a function, hello world, and we print it out. In the top, we import that and run it. And you'll notice when we inject our payload, which I'm not showing the code for this. You can see it in the GitHub repository if you'd like. When we do this, the payload is going to get injected into here, but the header itself is going to stay the same. So is it playing? Yep. Okay. So we run sample app. We get hello world. That's normal. That's nominal execution. And then we're going to go and inject our bytecode. And you'll see the payload changes, but the header stays the same. And then we go ahead and run our app again. And this time we get a calculator because we've modified the payload. Right? So this change is very important. Notice that the source code didn't change. Right? The source code in the library stayed exactly the same. And if you were actually to keep running this, it's not going to overwrite your cache because it still thinks that it's consistent. And so this is significant, right? Because if you look at the way that we handle packages, in Linux, if you've ever seen this message, running pip as the root user can result in broken permissions, that is because when you have globally installed code, multiple users can access that same code. And the problem here is that this results in privilege escalation if we have the ability to modify the cache, and then a different user runs it, thinking that the source code hasn't changed because the source code hasn't changed. And so this is a problem on Linux when people make mistakes installing packages, but on Windows, it's a problem all the time because that's the default way that pip works. And so if we can modify package code or package cache for any of these libraries on Windows, we can get privilege escalation between accounts, or at least lateral movement, assuming that root isn't running these things. And so this scored at an 8.4 on the CVSS scale. I don't necessarily think that CVSS is probably the best way to evaluate some of this stuff, but at least it is representative of something moderately significant. And so how do we fix this? So in principle, all we need to do is validate that the header is representing the actual cache itself. The problem here is that this is computationally expensive because we need to either somehow recompile portions of the source, or we need to somehow validate the cache at runtime. And this defeats the whole point of having the cache in the first place. So some of the ideas I have here, and I'm open to suggestions from folks at the end. I'm very curious to see what people think about this. There may be ways to validate either just the symbols that exist. So if we can validate variable names or class names, that might be enough. But you can still modify certain things with the same class names. So there's some amount of check that has to be done here. And we could do something like just-in-time checks or lazy checks, but then you're vulnerable to time of check, time of use stuff. So this is a little bit more complicated than it sounds probably, or maybe I'm overlooking something, and if anybody has ideas, I'm very open to them. But this is kind of where we're at. I think that there's probably a way to fix this. It just may be somewhat expensive depending on how it's done. And that brings us to our second issue. So, how are we doing on time? Okay, yeah, we're good on time. So, the second issue is in another sort of optimization that Python does. It's the stable ABI, or the C API for Python. And so this allows us to write code in C, compile it, and then run it in Python natively, or run it locally in Python. And so we're going to talk about what foreign functions are and how you would do this, why it's really beneficial, and show some of the performance benchmarks. We'll get into the vulnerability itself, and then we'll talk about impact and remediation of the issue. So foreign function implementation in Python. You have a couple ways to do this. So the problem we're solving for here is that Python, again, is pretty slow compared to C. And this is, again, because it's expensive to create stack frames. Usually this is the reason. There are a variety of things that can result in this. The way that we optimize code can be a factor. But usually it's just because of the stack frames. Python's abstraction, of course, is super helpful. Like, it's way easier to write Python code most of the time than C, or at least faster, depending on the use case, right, if we're writing a lot. And then even cached, bytecode has to be interpreted by the CPU. So we need a way to bypass this if we want to run C code, right? Because we're not generating bytecode, we're actually generating compiled C. And so for heavy math and science, things like machine learning applications, or any of so TensorFlow, for example, is done like this. And so generally we're going to write C, we're going to wrap that, and then we'll run it in Python through calls. And so again, the point here is that instead of interpreting bytecode, we're running compiled like C. And so we can use C types to do this for native libraries. So like if we want to run a time function out of libc, we can do that with CDLL. But if we want to run our own code, then we need to actually get into the API. All right, so what does this actually look like? Like, is the impact here that significant? As you can see, we have a very simple loop that is going to go 1 to the 9th power. And each loop, it's just going to divide the index by 5 and set that to a variable, or an integer 5, or an integer x. And so this is implemented in C on the left and Python on the right. And you'll see the native implementation in Python takes 32 seconds. The C implementation takes 1.6 seconds. So this is a huge impact for these kinds of libraries. Okay, and so one of the problems that we face here is that as you run code through the library, as it changes, right, it's from like 3.3 to 3.12 now, things change in Python. And so we need something to stabilize the changes between versions, and that's why the stable API was developed. So this is a more stable version of the C API for Python. And the problem here with most of these things, as any vulnerability in any protocol, is that it is really hard to change stuff unless you can ensure backwards compatibility. And the specific issue that we're talking about here falls into this category for a specific reason. We'll talk about it in a second. And so it is unlikely this will ever get fixed in Python 3. If there's a Python 4, maybe we see something then. But in Python 3, it's unlikely to get fixed. I think I'm going to skip the slide because it's not super important. This is just showing how to set up a foreign function in C. It'll be in the reference if you would like to see the slides after. And so this is what our threat model looks like. We have input gathered, same kind of thing, right? So we can cross all this out, and we're just looking at the libraries themselves. So we can modify the libraries, any input the libraries handle, anything the libraries are doing. Debatably, you still have some amount of input here if that's how you're going to attack the vuln, but like realistically, it's probably coming from something native to the C itself. And so you go right from libraries down to execution of the code. And so with that in mind, we want to identify an issue in the ABI itself. And so we're going to harness this through some amount of input, which we'll talk about in a second. And then we're going to write for an execution potential. So what this means is that we want to think about like what the impact that would be relevant and interesting would be. And so in this case, if we can get code execution that might be interesting, more realistically, even a denial of service here is probably more important, because if we have a multi-threaded app, this is handled by the parent thread. And if we can get it to segfault, we're going to kill the entire process from the parent level down, and we're going to crash the entire app, not just the handling of that specific library. So any exception handling that you have for those issues is not going to catch, and you're going to end up with a crash, and the entire app's going to go down. And so back to our fun code comments. Here we have a user. I'll read it to you because it's probably too small. N. Norwitz. Says that he needs to check for overflow, and this is on the production branch. And yes, he does, because there is an overflow here. And so we can use this memcopy and overflow it. Specifically, we'll talk about exactly how we get to this in a second, but we can overflow this memcopy, and we can use that to get a crash. And so the issue here is essentially that what we need to do to access this is set up non-contiguous memory in C. And so if we have like an array laid out as a block, blocks side by side, this will never hit. But if we have the ability to lay out blocks of memory with gaps, so you can think of this kind of like the heap, if we can lay out memory with blocks that have gaps in them, then it becomes a little more complicated to perform this copy, because we have to parse through memory to find the data that we actually care about, and that's where we hit this code. And so there's a number of dimensions field that is here on the bottom. So this ndim field specifies the number of dimensions in the array, and this is what we're going to use to overflow. So if we specify a 6-dimensional array into a 2-dimensional array, we're going to either get an out-of-bound read or an out-of-bound write, depending on how we do it. And as you can see, obviously there's no video for this because I don't think it's that interesting to just run a command for you guys. But we compile our foreign function, and then we have an out-of-bound read here, because we have two arrays that are 2-dimensional, and we're reading. We modified the second one to be reading in 6 dimensions. So it's going to read extra memory into that 2-dimensional array in the second phase. And so you can imagine there's leaks here. But what's more interesting is we're just going to overwrite the return pointer, and we're going to get a segmentation fault. And so we crash the parent process, and we kill the entire app, as opposed to just getting an exception here. And so I don't think the impact of this is super high, because the complexity of actually getting control here is pretty high. It's kind of challenging to find a point where we're going to be able to modify stuff to a sufficient degree. But if we can, we do get a crash. The other thing here is we're probably not going to get code execution through this bug. And that's granted, to the credit of the Python team, they have all memory protections on these binaries. So you can't just execute code on the stack. You're probably not going to build a ROP chain easily. It's going to be fairly complex to actually get code execution out of this. Never say never, right? There's probably a way, but it's not going to be as easy as it maybe would be in other cases. And so denial of service here, a crash is probably the best outcome. And that brings us to our third component. So those are both in native CPython code. This last one is in pip package management, and it's more of a discussion around how we handle packages in Python, rather than specifically a bug in pip itself. And so we're going to talk about how package publication works in Python, how like you and I can actually go and publish code to pip and then download it, what validation and checks happen. So there are some validations that happen here, both when the binary gets uploaded and then when it's actually in the cloud. And then the last thing is just the impacts and maybe ways to handle this problem. Okay. So it's super easy to publish a package. You guys can learn how to do this in 15 minutes. I'm sure many of you already know how to do this. And so we just basically set up requirements.txt, as you would with any Python project. And then you have the setup.py that contains a harness to upload to PyPy. And so we can generate this. We can run it with setup.py. This will generate a tar archive. And then we can take this and use Twine to upload it to Python. And so we can test this locally and then push it up, but it's super easy to do this. And I would encourage you guys to play with this. It's kind of fun to work on a package and then publish it. And so there are some checks that happen here. We do have consistency checks, so it wants to make sure that the source that you're actually pushing is represented in any sort of checksums that are set in the setup. It also is making sure that any of the required libraries, the versioning is correct for those, so the requirements actually are supported. And then it's going to push that package up. On the security side, it does some amount of checks for malicious code, known vulnerabilities, and it encourages code signing, but it doesn't enforce it. And so this sounds really good. Like, this sounds like it should cover us for most things, but it does not. So as you'll see in a second, we can push a pretty trivial reverse shell up, and it'll accept it without a problem. And so when we look at our threat model, now we're all the way up at the top. We're looking at the actual pip install command that happens, that the user runs, or the requirements file to actually get that versioning down. And then we have to go through all the steps to get execution. But we're actually controlling this outside of the loop here, so it's okay, and we don't have to deal with as much abstraction. And so this is what the demo looks like. So this is actually not true. I removed this, so you can't download it and play with it yourself, but if you want the code, it's up on my GitHub. And so steps to replicate, I would set up a virtual environment, and then you can install the Typosquatting library. You're going to listen for a shell and catch it, and that's what we're going to do in this video. So in the real world, this would be typosquatting something like the PIL library. So this is demonstrating instrumentation of the PIL library, or imaging manipulation in Python. So if you've ever done like import PIL, this is what we're talking about. And so we would typosquat something like 3 L's or 2 I's or something like that. And so here we go. So we're going to start listening for a shell. And then on the top, we're going to install the library. So I called it this is malware with underscores. And then you install it. We're going to run the interpreter. And we're going to import the image methods from PIL, because remember this is just PIL instrumented. And then we're going to take that and we're going to run our instrumented function, which is .open. And you'll see we catch a shell here. And this is a valid shell. And we're able to control system. And so what's important to mention here is this is a fully functional PIL library. If we spend the time to actually subprocess this and make it invisible to the user, they're going to have no idea that a shell was sent out unless some sort of malware software or something catches this, which we can certainly avoid. And so this is pretty significant. A lot of us might be thinking, well, I'm a really good keyboard user. I would never typo a library and install the wrong library. Unfortunately, though, this is very effective for bad people that are interested in doing malicious things, to the point where Python had to remove over 500 malicious packages from the repository last year. And we were seeing impacts in the sense of things where like people were putting up code that would change like crypto addresses. And so you would go to like put a crypto address in, and at the last minute it would switch it out for a malicious one. And that would end up then sending whatever token you're talking about to a malicious wallet address instead of the original one. So this is very real. It might sound kind of ridiculous that somebody would install something like this, but there's very little protection against uploading typosquatted packages, and it's this easy to instrument them. And so the problem here is that Python doesn't do necessary checks, and they can't manually review every single package that goes up because the team is very small. Again, their total gross revenue for the company is $3 million a year. They probably have a handful of people on staff. I think they've got like 1 or 2 security people. I don't know these things for sure. This is my assumptions based on what I'm seeing when I interact with them. And so the problem here is like we can't do this manually. So I think there may be something interesting here around like large language models. Maybe there's a way to compare code. So like let's say we shouldn't be able to upload a package that's 99.5% representative of something else, right? Like if we're uploading Pillow, but it's like one thing has changed, that should probably at least get flagged for a person to review, right? And so in this sense, there's probably some version of an LLM that we could use to verify packages. I'm, again, curious to see if other people have ideas here. I'm happy to take those at the end and see if we can maybe iterate on this and find a better solution. The other thing here that I think is significant is adding checks for well-known malicious code. So you can see it again in the GitHub repository. The reverse shell that I'm catching here is like the native Python OS reverse shell that you could find on like Hacktricks. It's super well-known code. This is not some novel like crazy like memory manipulation thing I'm doing. It's very, very straightforward, and it should absolutely be blacklisted. It should not be allowed, or again, at least flagged for a human to review. Maybe there are legitimate use cases in certain scenarios, right? But a human should have to review this if it's this kind of thing, because it is significant. And even though they don't have hundreds of people, they do have enough people to review a flagged package once a week, probably. So, some closing thoughts. I wanted to just step through the methodology again, so how I found some of this stuff, and then talk about some future work or things that I'm interested in working on and maybe could use some support from the community. And so, the biggest thing I think when looking for bugs in any software, whether it's open source or closed source, is just having some amount of product comprehension. So, if we don't understand how the product works, it's really hard to find bugs in it. This is pretty logical, but a lot of people do overlook this, or they don't spend enough time actually understanding the software that they're trying to find issues in. This is something that I really push on the junior engineers I work with, and I think it's really, really important. You need to understand the software you're working with, and that's going to lead to actually finding the critical issues. And so that's why we spent so much time at the beginning on how CPython works and some of these optimizations, because if you don't understand them, you can't exploit them. And then after that, I think having a framework to understand where we can input and what we get out is useful. So this maybe isn't a requirement, but I do think some amount of threat modeling is helpful here. And just having a rough idea for where we can control stuff and where maybe we get outputs, whether they're processes or manipulations of devices, or even just files on disk. And then lastly, this is something maybe I wish I had worked on a little bit harder for this talk, but working on impactful bugs first. So thinking about what portions of the code base are going to have high impact vulns. So I think going after things like, again, like the HTTP libs or SQL libs is probably interesting because it's going to involve some amount of interaction with a remote device. And so a lot of the time, those are the kinds of things that are actually going to give you, unauth RCE, right? That would actually be like legitimate CVSS 10s that the PSRT team would probably want to fix. So I think looking for impact first is really important, and so maybe something I wish I had done here, but for future work. And so on the topic of future work, I think that there are some ML AI implications or things that we can work on in this sort of large language model space that would be interesting for Python. I think I'm personally just interested in a lot of the machine learning stuff that's happening. I'm sure a lot of people are here. And I think specifically for these small teams, it's really useful because you don't have a lot of people, you don't have a lot of resources, and maybe you're not going to get 100% accuracy, but you can at least probably flag with near 100% accuracy and then have a human do the last step. And so you can probably get a huge security improvement with some amount of this, and I'm curious what kind of projects people are thinking about, maybe some ideas here. And so whether this means offline models or some of the more closed source stuff that like OpenAI is developing, whatever it might be, lots of options. And then I think the other thing that's really interesting that I haven't really come up with a solution for is the prevention of security disclosures via code comments, because this is something that plagues Python across all sorts of code, across all of CPython, and I think that we probably should be more careful about uploading just, hey, there's a vuln right here kind of code. So maybe there's a large language model solution to this as well. I don't know. Maybe there's something else that we can do here. But I think that's something that we can work on as well. So that's all I got for you guys. If you would like to get the code, I have it on my GitHub at the top. You can take this QR code and use that to get access to the slides. I need to update the GitHub repository in a couple of minutes. I haven't done that. But I'll put the slides on GitHub as well. So thank you for your time. I appreciate coming to the talk. And if you have any questions, I'm happy to take them now. All right. Thank you guys. Appreciate it.